And hello, welcome everyone. So last video we were doing this part. Let's see. Yeah, we're doing this. So Control up, Control down, Control up, Control U, Control D to scroll in Vim mode. Yeah, we pretty much ascertained that the MockPipe result and the nonlinear resistor reference result are pretty much the same. I just skipped the fact test after that. Today, in this video, we're going to talk about the PipeFactory. The PipeFactory will help us to instantiate various implementations of pipe. So I'm going to have many versions of my pipe code. Okay, I'm going to load the file. Now I'm going to have many versions of my pipe code. So this is the MockPipe custom resistor, so it's nothing but the custom resistor. I just changed the names, that's all. Yeah, but I'm going to want to add a lot of things in. For example, my partial derivatives. I want to add my friction factors and everything. So yes, how would I do that? Okay, so first is that I will make many different versions of the pipe. So I will have like a MockPipe factory. It is basically a vanilla thing. Then maybe I'm gonna have one with Reynolds numbers. I need to calculate friction factors. And then the next one, maybe I need to include height elevation, and then temperature differences, so on and so forth. Those are the things I have in mind. Okay, those are the things I have in mind. So I'm not gonna add everything at one go because it's gonna rather I'm not going to have my pipe class perfect at one go. It's going to go through many rounds of testing and changing. That's why I need to be able to swap it out, swap in and out the pipe classes very easily, so that I have many different types of components I can test. Okay, so this is what the PipeFactory is. Okay, so the way to use PipeFactory is this. I will have a PipeFactory class. It will be of the object type PipeFactory. Okay, and then you just instantiate the new PipeFactory class like that. Okay, the name of the resistor is the first argument. Okay, and the A node, the name of the node A in that resistor is called out. The name of the A node in the resistor is called out. The name of the B node, that means the outlet node, so to speak, where the current's coming out of the resistor by convention, that will be called 0. Okay, and then everything else here is the same. Oh, I'm referencing the wrong one. Yeah, so again, R and L1, out and 0. Okay, so the next step is to use the returnPipe method. Okay, the returnPipe method is called MockPipe custom resistor. Okay, MockPipe custom resistor. So MockPipe custom resistor is the class type, and the return type of this method is component, right? It is component because all my pipe classes will inherit from component, so that's why I type it as component. However, when I use the component class, I will not be able to. I will not be able to, let's see. Yeah, I will not be able to access the base parameters. Okay, if you take a look here at components and you look at component.cs, okay, component.cs is right here. Okay, I'm gonna try opening it up. Maybe I'll just quit. Okay, I'll just say it's here. The component.cs is here. It does not, within the component CS, if you scroll through this file, I'm not gonna, okay, maybe I should scroll, right? I should scroll. Okay, let's see if I can go to component.cs. I'll make a tab new nerd tree, and then the first thing I do is set number, set relative number. Okay, so at least I have my numbering system here. Okay, I'll go upper directory, I'll go upper directory. Yeah, I'll keep going up and I'll go to SpiceSharp and I'll go to the components. Okay, I'll go to Shift C to make this my root folder. And next thing I'm going to open up is component.cs. Okay, component.cs is an abstract class. Okay, unfortunately in this class you will not see any sort of base parameters in here. Okay, no base parameters are in here. You can see the rule subject apply. There's another abstract class with some parameter type. Okay, you will not see any method or property that talks about this thing called parameters. Okay, parameters only works in this class. Okay. Okay, in this class, yeah, parameters is only accessible within this MockPipe custom resistor class. It is not accessible within components. So the few ways, of course, one is to make another kind of a class which tries to inherit from component, and then it has this parameters object, and then I can change the properties within the parameters object. And well, frankly speaking, I don't know whether that is desirable. I don't want to change too much in the code. I don't want to make so many new class types that it becomes again hard to read. So try to keep it simple. So what do I do then? Okay, the thing now I do instead is to just okay, the return type of this PipeFactory, if you use the return type, return pipe code is called component. Yeah, it's component. Okay, but this component can be cast. Okay, can be typecast as a MockPipe custom resistor. So I'm changing the type of this pipe. I just call it the precast pipe. I'm changing the type of this precast pipe to this thing called component. Okay, I'm changing the type of this precast type pipe. I'm changing it to component. Okay, so that's the whole idea here. So components, precast pipe component, it will become my MockPipe custom resistor type. So I am changing the type of this precast type from component to something more specific, which is a MockPipe custom resistor. So this thing, if you didn't already know, is called typecasting. I will not explain too much on that here. So once I am in the MockPipe, okay, I'm at the MockPipe resistor type, I can start doing things as per normal. I can connect the nodes. I can set the parameter A and B is something, and then I will just, you know, I will just do this as per normal. Okay, so where is this done? Okay, so I better silence the phone. So yes, there's a friction factor. Yes, when here is where I have my real class here. You can see that this DC voltage here is being swept from 1.45 volt to 1.5 volts. Okay, and then yeah, I'll just put this .c out. Okay, MockPipe class with PipeFactory. Yeah, so that you can see where this is coming from. Yeah, and I forgot my semicolons. Okay, so MockPipe class with PipeFactory. You can see that these two results are given here: 5.25 times 10 to the minus 7, 5.62 times 10 to the minus 7. Now, so this is the this is the reference like value. Okay, and then let's see. Now this is a reference value, and well, my so-called well, the normal way of making my MockPipe, we already tested, is that it's pretty much the same as our what do you call that? We have tested that it's pretty much the same as our nonlinear resistor, so we kind of know it's functioning correctly. So yeah, the normal way of instantiating the class is over here. Okay, so I'm just going to open up and I'm going to put this .cout C out what? I'll need a string here. It'll be just a MockPipe without using PipeFactory. Yeah. So if you examine the code, what for the PipeFactory, let's go to line 370. Okay, line 370 is over here. And I forgot semicolon again. So you can see that the pipe resistors, the MockPipe custom resistor has a parameter A2 times 10 to the 3. B is 0.5. The circuit is just a voltage source and the MockPipe. Okay, the connection nodes are out and 0. There's nothing else there. Okay, the DC sweep is from 1.45 to 5. Everything else here is the same. I do not want to touch it. Now, if you take a look at look at the PipeFactory. Look at the PipeFactory. Yeah, you can see that the settings are pretty much the same. My MockPipe is 2000. Parameter A is 2000. Parameter B is 0.5. It's connected to out and 0, as you can see over here. Yeah, it's also connected to out and 0 here in the MockPipe. Okay, and yeah, so this is the factory mode. Circuit is the same, voltage source and MockPipe. The DC sweep is in the same voltage range, and then everything's the same. So you can see that the MockPipe class with PipeFactory is this much. MockPipe class without using PipeFactory is this much. Okay, so I just called this the sandbox mode. Okay, why do I call it the sandbox mode? Yeah, let me start adding things in. Now, why did I call it the sandbox mode? Because when I actually play around, yeah, this is called the sandbox print result. Yeah, when I was actually doing this thing, I was trying to experiment with printing results from inside the simulation, as in the simulation data over here. And see the simulation data here, it's referring to the current flowing through the voltage one. Okay, so this is the current export part of the code, and then it says what, export simulation data. I want some way of being able to extract this currents from the circuit. I have not really found out how to do it, so I just made a test called sandbox. But in reality, this sandbox is just another way of maybe I'll X this out. I'll paste it. Okay, I'll paste it over here. Okay, MockPipe class built without factory, reference for factory class. So what am I trying to test here? Okay, I'm trying to test that if I use the factory class to build a MockPipe with exactly the same parameters versus I'm building it manually, I'll get exactly the same result. Okay, and of course you can see the source code a little bit later, but for now, not yet. Okay, so this is MockPipe reference for the no factory build. Okay, MockPipe reference no factory build. Okay, I'll just call it MockPipe reference no factory build. I'll call this the no factory build test. Okay, so MockPipe class with PipeFactory, using PipeFactory and MockPipe reference no factory build. Okay, see the voltage results are pretty much the same. So I'm going to copy, of course, all of these results over here. Okay, so factory. So it shows that the factory works. Okay, here I'll say here are the results produced. Okay, and now I'm going to put a code block with a Z shell. Okay, I'm going to insert here. Oops. I'm going to insert it here rather than in VS Code, because at least I can paste using the Vim registers. Okay, so I'm going to copy the results here using the no factory build. Oopsie. MockPipe class no factory build. This is the... Okay, I'll need to copy slowly, and I'll yank this. I'll go over and I'll paste it here. And then what else is next? Okay, for reference, here is code that builds MockPipe without the factory. Okay, this is MockPipe without the factory, and I'm just showing that it works. Okay, so I'm going to build some C# code blocks, and then I'll put it here. And then what I'll do is that I will say, yeah, okay, I'll go down 30 lines, yank this, and I'll paste it here. I'll go down 30 lines, and I'll indent to the left. Okay, of course now I can't see anything yet, which is fine. And this is the no factory built version. Okay, so 32 down, ZZ, open, Z shell, code block close, and here are the results for the no factory build. Okay, I used print. I used print at this time rather than assert, because I don't really know how to extract data from simulations yet. Okay, okay, and just to really show that it really works, okay, MockPipe reference no factory build. Okay, I will make one more. I'll make one more. I'll make one more class that says, okay, nonlinear resistor reference. Okay, so this is the nonlinear resistor reference. Just want to be superbly sure that it's all the same. So let me go and look for a nonlinear resistor. Okay, nonlinear resistor. Okay, then I'll put it inside. Okay. There's the MockPipe reference, yes. So nonlinear resistor, wrong pipe type, catch exception. Where is it? Where is it? Oh, mock. Oh, right. I literally copied and pasted everything. That's why. Okay, that's better. MockPipe reference no factory build, and this one I'll change it to non-linear resistor reference. Okay, no factory build. Okay, I will change this thing here to NLR for non-linear resistor. I'll delete the MockPipe entirely. Okay, and then I'll call this the non-linear resistor no factory build. Okay, so this one is it is as vanilla as it gets. However, it has the 1.45 to 1.5 volt DC, you know, DC what do you call that? Yeah, DC voltage sweep. Okay, and now of course, you know, the results are getting cluttered. As you can see here, it's getting all cluttered and it looks very messy. So I think I'll opt for, you know, putting some spacers here. Okay, with a /n in front. I'll put a /n over here. Okay, then I'll just put a /n right here. Oh, right. Okay. Yeah. Okay, so this is slightly neater, but I think I still want to have a space behind. So I'll just do it like so, /n. Okay, the /n here. And last one, it will be a /n over here. So at least it has a space before and a space after. Okay, so MockPipe without using PipeFactory. Okay, nonlinear resistance, no factory build. Okay, MockPipe reference, no factory build, and okay, MockPipe reference, no factory build. You can see this test is actually getting more and more crowded with a lot of print statements. So generally speaking, don't like to put too much print statements if possible. But again, for now, it's a very rudimentary way of testing. It's manual testing, but okay, at least it shows that everything is checks out. So I'll just update the code again. Okay. So MockPipe class with PipeFactory. I'll paste it here. Indent it in. Okay. 30 down. Exit out. Okay. Then the no factory build class will be here. 30 down. GT. So this is the MockPipe class without the factory. X and okay, the results are the same. Okay, to really hit the point home, I'm going to test it with a nonlinear resistor. This is the vanilla code. Okay, there you go. So let's see. So this is the nonlinear resistor vanilla code. Okay. C#. Okay, so let's go 30 down, indent. Okay, and then let's use the nonlinear resistance, no factory build. Use visual mode. I'll copy the result here. Okay, 25 down. Okay, Z shell. I'll paste it here. Oops. Paste it here. Alright, so I think I'm happy. I can go to VS Code and see what the thing looks like. Because it automatically update. I'm having the same file open in Vim and VS Code. So this thing still works. You see the thing actually works here. Non-linear resistor reference, no builds. Okay, so let's put here that and here are the results. So yeah, everything checks out. Everything checks out. Okay. Alright, so now let's go on to the next part of the tests. It's for this one I want to close. Oh shucks, I closed my whole browser. Oh, whatever. I should just press Ctrl W, but doesn't matter. For the sake of this video, let's just go for the Churchill correlation. Doesn't really make a difference. So next bit is to start making classes. Alright. Next bit is to start making classes and functions for estimating the friction factor. So I made a class for that. And here are the tests for this class. I will tell you the inner workings later. So I use the Churchill correlation as the basis because it's not piecewise like other functions, meaning to say that I don't have one equation for the laminar region, one equation for turbulent region, then another equation to like interpolate in between. It's just one smooth equation. Okay, that's a nice thing. So to test for laminar, where is it? MockPipe result, PipeFactory. Maybe I should use this part as the yeah. Control up, yes. So okay, to test for validity within the laminar flow regime, I do use the laminar flow equation for friction factor 16 over RE. Okay, so that's the idea over here. I keep scrolling up and down, my goodness. Okay, so oh yeah, I do have to do a git add later. Okay, so how does the code work? Okay, how does the code work? Okay, let me remove this. If not, the sentence doesn't really make sense. Okay, how do I do this? Okay, I'm using a theory test. Okay, so this one is more standard. I keep going up and down. Right. Okay, here it is. Yes. Let me use a different one for preview. Okay, now things are in sync. Oh, I think that's why I've been editing in Vim and not here. That's why I have to close and then open again. Okay, what I meant is that when I edit things here, okay, the preview and the text here syncs properly, but I've been editing all the text files in Vim. Okay, I'll load the file using L. I've been editing the text files in Vim, but that means that the preview between the text here and the preview of the markdown here will not be the same. So that's something to take note. Okay, so just close and open again, you'll be fine. The things will sync up properly in VS Code. But yes, here's my setup. I have my reference friction factor. Reference friction factor is 16 over the Reynolds number. Okay, that is for fanning friction factor in the laminar region. And then I have my friction factor object. Okay, this class will be called Churchill friction factor, and I have the interface I friction factor. Why do I have this interface? It's just in case I have different types of friction factor, different things going on under the hood. I use different equation, maybe Colebrook, maybe some other equation, and then I want to calculate friction factor, I can have that. Okay, so friction factor object equals to new Churchill friction factor. So the result friction factor is friction factor object fanning. I supply the Reynolds number and the roughness ratio. What is the Reynolds number and the roughness ratio? Okay, Reynolds number and roughness ratio will be supplied in the function here. You can see that there's a double Reynolds number here. Okay, double Reynolds number here, and double roughness ratio here. So two things are supplied. So I supply the Reynolds number from 100 all the way to 2200, and I change the roughness ratio along the way. Okay, it should not have any impact in the laminar region. So I actually just for that, I changed the roughness ratio from 400 over here. I mean, oh no, not 400. From 0.05 here at Reynolds number 400 to 0.0 at Reynolds number 400. Okay, what is my then after that, yeah, I'll get the result friction factor, and then I will compare the two to try and make sure it's within within 10%. Okay, so result error fraction is, how do I calculate it? I calculate it as the difference between the result friction factor and the reference friction factor. I'll take the absolute value of that, so it doesn't really matter which one comes first. Of course, reference reference friction factor can come after. Okay, and I divide it by the reference friction factor. Okay, this one should be positive, but just in case I can have a math absolute function at the bottom, so it's more general, but that's really not needed. Okay, so this is the result error fraction. Okay, I want to assert that this error fraction is the same as 0. That means the error is as close to 0 as possible within one decimal place. Okay, if it's within one decimal place, meaning to say if this thing is 0.09, it will run off to maybe 0. Okay, run off to maybe 0. Okay, or maybe 0.1. I'm not really sure how the rounding thing works. But in worst case scenario is 0.099 and it rounds off to 0, I still have asserted that the friction factor correlation is accurate to within 10% up to Reynolds number 2200. So Reynolds number here 2200. So theory tests, they help us with this to automate, and this thing passes wonderfully. I don't have any errors and I don't need to print out statements and anything. Okay, so you can see that this assert equal is done. Okay, once I'm done with this, I wanted to see how accurate this equation was. So I do pretty much the same thing here. And I stipulate, okay, that instead of rounding off to one decimal place, I say that the max error fraction is 0.04. Okay, I will calculate my error pretty much the same way. My result fanning and my reference fanning friction factor is the same. And I'll say that, can you assert that the error of this of the calculations here is less than the maximum error. So it is true that is less than the maximum error up to Reynolds number 2200. Okay, so that's okay, that's perfectly fine. Okay, because around Reynolds number 2200, 2300, it starts transiting to the transition region, so that laminar flow equation doesn't really work anymore. Okay, as a last note, just to make it more stringent, okay, because this is a 4% error max, I want to make sure that this equation, Churchill equation, is accurate to within 2% for Reynolds number less than 2000. So I changed the error max to 0.02. You can see that the maximum Reynolds number here is 2000. Reynolds number here is 2200. So actually within Reynolds number 2000 and below, the maximum error is 2%. So I've done that. That is good. And then for the turbulent region, I wanted to do a similar test. Okay, that this thing is within 2%. Okay, basically within 2%. Okay, again, how do I select my values? Okay, so what I did here was to go to engineering toolbox. Okay, this is one of the things here. Okay, let me open up engineering toolbox. Friction factor. Okay, and then I will go to Moody diagram. I'll go down. Okay, oh, not this page. I'll use the Colebrook equation. Yeah, Colebrook equation. See, there's an online Colebrook calculator which I use here, and then there is some Moody diagram here for which I can quickly reference. So let's take a look at the first data point, which is 4000 0.05, for Reynolds number of 4000 and roughness ratio of 0.05. So to make the roughness ratio 0.05, I just set the hydraulic diameter to 1, roughness of surface to 0.05 meter, Reynolds number 4000. Okay, this is a very simple point. And you can see that the friction coefficient here, which is the Moody friction factor, is 0.0678. So let's see, I'm having the same document over here, 0.06789 blah blah blah. Okay, so this is one of the ways. I'm pretty much, there's a Colebrook formula calculator that does a little bit of a better job. I think this is it. So absolute roughness 0.05. So you can see I've visited this one before. Reynolds number 4E3. You can see that the Darcy friction factor here is this number. So I basically copy and pasted this number put it here. Okay, so that's how I did it. Okay, so why did I use 0.05? Right, 0.05 is a very rough surface here. Okay, well, I cannot quite see where it is at 4000. I can see it's somewhere in between 0.07 and 0.08. Okay, a little bit more than 0.075. So that's your sanity check. I'm able to read. So this is actually 0.0769. So that's within the correct range of this chart. So that means that calculator kind of works, assuming this chart is correct. And then yeah, I put it in here. Okay. Next thing is to have the same thing at 4000. I use the same 0.05 curve. Why? Because I wanted to see whether, you know, well, for the first series of tests, it's easy to see that after maybe about Reynolds number 4 times 10 to the 5th power, or maybe 4 times 10 to the 4, you see it's this line here, you go all the way up, it's already more or less constant, and it's maybe around 0.072 or 0.074. Okay, after a while, you keep increasing the Reynolds number, all the friction factor has to remain constant, because this is a very, very rough pipe, and this is the rough extreme part of it, and I want to make sure that the Churchill equation works for that. And not only that, if I start with this, I can pretty much be sure that the friction factor is more or less the same all the way through, all the way up to 4 times 10 to the 9. Okay, 4 times 10 to the 9. So you can see that I do 40,000, 400,000, 4 million, 40 million, 40 million, 400 million, and 4 billion, the Reynolds numbers. You can see that the friction factor more or less stays the same, 0.0715, 0.0715. Okay, it keeps staying the same, and that makes it very easy because I do not need to keep checking back with this graph, and I know that the friction factor is more or less roughly the same. So these actually make it very easy points to test this Colebrook relation. Okay, so this is how I test the rough part of the pipe. And then what do I do next? I want to look at the smoother part of the pipe. So I just go straight for zero roughness at all. Okay, zero roughness will be somewhere here. You can see the friction factor is somewhere in between 0.04, 0.05. So this is the other extreme. And the other extreme is here. And then 0.0, and then the friction factor here is maybe 0.04. Okay, so this is a smooth pipe. Okay, smooth pipe. So this one is saying what, 0.039 or something like that. Okay, so and a Reynolds number of 4000. So again, very hard because in the transition region it's very difficult to see anything, but yeah, okay, let's put it at 0.0, 4 times 10 to the 3, and this is where I got my answer from for the Darcy friction factor. Okay, this is as extreme as it gets. It's in the transition region. It may not even be that, or rather just going out from transition region to turbulence may not be superbly accurate, but this is for smooth pipes. So all the way at the bottom, you can see that the coefficient of friction here is very, very difficult to see. Okay, so but you can kind of accept it's within that range, so you just leave it as it is. Okay, go to the other extreme for 4E7. So this is where it is, 4E7. 4E7, I can look at this graph, I see 0.0005. 0000. So 4 zeros, okay? 5 times 10 to the minus 5. Okay, what's the friction factor here? Okay, 4 at 4E7. 4E7. So you see this line 4E7 here at 0.005 is very close to 0.01. Yeah, you see this friction factor here, very, very close to 0.01. In fact, just a little bit more. So do we get a little bit more? We do get a little bit more. If we do that, so it's 0.0005. I put 4E7, calculate, and there you go. It's just slightly above 0.01 for Darcy friction factor. So it's not fanning anymore, we are using Darcy. Okay, so here are some data points. Again, 4 times 4e6. So where's 4e6? 4e6 is here. I look for an easy point, 0.01 or 001. So 4e6, somewhere here. 0.01 is this curve. You can read it as 0.02 something, maybe 22. Okay. Oh, right, sorry, 4e6 and 0.001. So somewhere here, very close to very close to 0.02, and the roughness ratio is 0.001. You have almost 0.02. Okay, roughly. That's roughly, get it? Never mind. 0.001. Calculate. Okay, it'll be this much. I just trust this calculator. I hope it's fine. It uses the Colebrook relation. I hope it's accurate. So it's more or less okay. It kind of corroborates with this chart. Good enough. Yeah, that's fine. Next point, 4 times 10 to the 5, 0.01 roughness. So this is the 0.01 roughness. 4 times 10 to the 5 is somewhere here. Somewhere here. So it's 0.03 something. So it's 0.03 something. As you can see on the graph here, 0.038 according to the calculator. Last point, 4 times 10 to the 4th. So somewhere along this line here. Okay, not very good at tracing, but roughness ratio 0.03. Again, fully turbulent region. You should have friction factor of almost 0.06. So we have a friction factor of almost 0.06. So all this becomes my data points, which I manually read, manually verified by looking at this chart, and then I use this calculator here to kind of do what I need to do. Okay, so calculator. I use the calculator. I'll just put here to help me calculate the friction factor reference values. Okay, this is based off Colebrook relation or Colebrook formula. Right. So how does the test go? Again, I have the reference Darcy factor equals to the reference friction factor. That is actually just keyed in as the third argument. So see the third argument right here is coded in as the reference friction factor. The second argument is the roughness ratio, which I just keyed in here. The first argument, Reynolds number. Okay, Reynolds number. So I again instantiate my friction factor object. I say that I want my error max to be 0.02. Okay, I say that my result Darcy friction factor is this much. I have a Darcy function right here. Input the Reynolds number and roughness ratio, churn out the Darcy friction factor. I calculate error percent, and I verify that all of these errors are within 2%. Okay, so that's pretty good. Okay, we have verified our. This is how I verify my Darcy Churchill correlation in both laminar and turbulent region. Okay, so that's all I have. Next class. This is not class. Next video. I'll see you in the next video. Yeah.